In this video, we're going to be looking at exponential functions, and then we're going to be looking through an equation y equals to your a times your b to the x then plus q. And first, I'm going to explain these variables. Then in the second video, we're going to be looking at logarithmic functions, which are the inverse of exponential functions. So here I'm going to be explaining the variables, the shape of the functions, some reflections, as well as the domain and the range of the function. So we may also hint on whether the function is increasing or else it is decreasing. So without further ado, let's get on to it. So for the value of q, we notice that the value of q is what? It's a horizontal asymptote. And then it is not what? A y-intercept. So it is not a y-intercept. So it is very important to note that, because you have been having other functions like y equals to your mx plus c, whereby this value over there was representing a y-intercept. Just like in parabolas where you had your ax plus bx plus c, then this last term or last variable was rather what? A y-intercept. And it's important to note that here it's not a y-intercept but a horizontal asymptote. Now we're going to go straight to the shape of the function. That how does it really looks like? For the shape of the function, so we're going to have four shapes of an exponential function, and then I'm going to just draw them. We have an exponential function looking like that, or the exponential function looking like this. So the first one is an increasing one, because as x approaches infinity, y approaches infinity. You can see that the y values start off low but keeps on increasing, getting higher and higher. Remember that we read the graph from left to right, so they keep going higher, so they keep approaching a positive infinity. So we notice that this is an increasing exponential function. And then what we notice, or what I'm going to say rather, a here is greater than 0, but b is what? Is greater than 1. And what you also have to notice is that b cannot be equal to 0. Remember, we are looking at that expression or that equation y equals to your a times b to the x then plus q. And the value of a can either be positive or be negative. Let's look at another scenario. Here a is still greater than 0, but then b lies between 0 and 1. What we can also see is that as x approaches infinity, y approaches negative infinity. This means that this is what? A decreasing exponential function. Because as x approaches infinity, y approaches negative infinity. The simple way of looking at this was that this graph keeps on decreasing. So y keeps on going down and is approaching negative infinity. Okay, now we go to the third one. So this one is the first, this is the second. Now we can look at the third and fourth. So for third and fourth, we can just draw our q, because q for the first two have been the axis, the x-axis by the way, or to be specific. So we're going to be looking at a graph at a decreasing function looking like that. So we notice that this graph is decreasing. Why? It's because as x approaches infinity, y approaches negative infinity. So this is a decreasing function, and the better way of looking at it is just to say that looking like this is just keep on decreasing. So the y values keeps on going down and down and down. So it is a decreasing function. But what about the values of a and b? So the value of a here, it is less than 0, but b is what is greater than 1. So b is greater than 1, b is greater than 1. Then we're going to look at the second one. So a is what is less than 0, but b lies between 0 and 1. So how does it look like? We can even draw the value of q over there, and then we just draw the function. So it is still an exponential function, but the other direction around than the third one. So is it decreasing or increasing? You can see, since we read the graph from left to right, so the y values keeps on increasing, and they try to approach what? Positive infinity. So what we can say is, as x approaches positive infinity, y approaches positive infinity. So this is an increasing function. Although really you can say that we are actually more like approaching the value of q rather than positive infinity, but then we are approaching the value of q. But then I'm just showing you the idea of increasing function as well as decreasing function. So we're going to look at reflections of an exponential function. So, but then we're going to look at just two. So it will be the reflection about the x-axis and the reflection about about the y-axis. Then the reflection about y equals to x will be what will become a logarithmic function, which is what we'll deal with in the next video. So the reflection about the x-axis, you just take y and make it negative. So it's more like you let y equals to negative y. And then the reflection about the y-axis, you're going to let x be negative x. Let's talk about the reflection about the x-axis. Now first we want to look at the sketch. So we had a graph, original function, looking like that, and then if we reflect it about the x-axis, remember the x-axis now becomes what? The mirror. So we want to form the image if we look at the mirror on the x-axis. So there is the mirror, is the image, so the mirror image. So if this graph y, if it looks itself on the x-axis, so it appears as y prime. So, and what you notice is that the distance between the graph and the x-axis should be equal to the x-axis and the mirror image. So that is why in many cases when we are using reflections, we talk about about the midpoint. So we look at at the midpoint. So we use the midpoint formula to deal with the reflections. See, for example, now we want to prove why we take y to be negative y. So say you have this point being what? Being maybe negative 1 is to 2. Then the reflected point, you can see that this line is perpendicular to that, so it is -1, but now to what? To -2, because we are below what the x-axis is. And then you take this point. This point is very clear that it is probably 0 is to 1, and then this point should be what? Should be 0 is to -1. But what do you notice about the y values? The y values change from what? From positive to negative, which means we are right to say that we take y and we make it -y. So let's look at a function. An example, y equals to your 2 to the x, then plus 5. Then we want to reflect it about the x-axis. So remember, y becomes -y. So it's -y equals to your 2 to the x, then plus 5. Then to find y, which is not really now y, or else more like y prime, which is going to be equals to your -2 to the x, then minus 5 if you divide by -1. So what you see is the reason I do not say that this graph is y equals to your -2x minus 5 is because the first one is already y equals to 2 to the x, then plus 5. Then the reflected one, it makes easy to say that it is y prime, just to see that it is really not the same as what as the original function. Now we want to look at what is the reflection about the y-axis. Say we have a function looking like that. But then the reflection about the y-axis is pretty simple. First, you want to more like complete what? A parabola. So I'm trying to complete what? A parabola. So that the distance between the parabola is more like equal. Even though mine is not like equal, then I complete the shape for what? For an exponential function. So that is how you reflect it about the y-axis. But now the question is, why do we take x to be -x? Say this point is maybe, we can say maybe -1 is to 4. Then this should be what? This is the original point, and then this is what? The reflected point. So the original point is also on y equal to 4, but then now the x value is no longer negative, it's not negative, it is positive. So this point is what? Is 1 is to 4. So you can see that the x value for the reflected point, so this is the original point. Say this is point P. So this point will be more like P prime after you have just reflected it. So the original x value is positive, and then the reflected x value for the reflected point is what? Is negative. So you take x to be -x. So that is how you reflect about the x and y axis. For the domain, we're going to be using a vertical test, which is quite simple. So say you have a graph looking like that. So you want to throw out the vertical